So as we just saw, we can approach this topic in both in two directions. We can use the triangle and we can use the circle, and we need both. We need to but we need to start from a triangle because that is easier to deal with, and then we will move on to the circle model, and then we're gonna use it back and forth. The triangle is easier to visualize because it's there. It's just an object that you can visualize easily. But for the circle, you need like lots of lines. You need to also put it in the plane. There are lots of things going on there. But first, let's start from the triangle. Yeah, this triangle. Maybe not. Yeah, let's use some vocab just in case. But all we need angle, which is measuring the distance between two lines. If you put two sticks together and you want to measure how close or how far away they are from each other from this this common point, you can measure it using angle. And there are at least two ways to measure angle, and at least two units. We can measure using a degree, and that's the circle. We put over the number. Like if we can measure 30 degree, it's gonna be an angle. And the way we agree on the measurement is we let the angle of we add a full angle. Oh, we let a full angle if you rotate yourself for one full round. That angle is 360 degree. And once we have that, then we can describe other kinds of angles or of rotation. You can if you only rotate halfway, that's gonna be 180 degrees because it is half of the full rotation. It's half of 360, which is 180. And if it's half of that, then we have what we call the right angle. And the right angle is very important as we see in a moment, because that's gonna make our life a lot easier. Oh, and usually when you place objects together, you want to place them perpendicularly, perpendicularly, make a right angle. If you have something on the ground, you might to place a pole upright, the right angle. Otherwise, it's gonna fall down in one of the directions. Then we have a side. In this triangle, it has three angles, and if it has three angles, then it would have three sides. This is not obvious. We will find this out later in this course. But for now, we have three angles. This right, three sides. That's a triangle for you. And we are gonna focus on the right angle. And also the right triangle. Right, the right triangle means you have an angle. We have a triangle where one of the angle is the right angle. This one is the right triangle. It is a right triangle. Sorry. And this is the right angle, but the other two can be anything we want to. Not anything actually, but you will get there in a moment. Then we have some fact that you might have seen. It's not that obvious, but you can think of it intuitively. It's about a similar triangle. So if you have two triangle which looks the same, and they look similar, as the name suggests, and then we can derive some properties for these two triangles. For instance, if I use this software, which is OneNote, so let's draw some triangle. There it is. Looks nice. Notice that if I copy it, another triangle, and if I change the size, click on one of the pivot points and move it up and down, you can see how this new triangle behaves. It's larger, it's smaller, but one thing you can see for sure is that the lines on the left and the line at the bottom or the base are unchanged, and they are still parallel to the original triangle. Remember, we have two triangles. Oops, now we don't. we are supposed to have two triangles. Okay, they snap. Why do we have two triangles, and we change the shape, we resize, we scale it up, and we shrink it down, and they still preserve some properties. And there are several properties here. For instance, this angle stays the same. And the distance between these two, the angle between these two sides, they are unchanged. One way to see is that because we simply change this the opposite side, we only move this side, and so it shouldn't affect the angle. And that's one thing to see, but it's not a proof. It's just formal. Oops. So that's one thing we can see. Another thing is that the angles are also the same here and there. Which is it doesn't follow. Okay, like that too. Anyway, this angle is the same. Like we have the same angle here. If you move out, the line gets larger, but the angles are still unchanged. And again, that should make sense, right? Because we scale this up, then they should look the same. No matter how far or how short, how close, we move them. So these two are the same, and these two are also the same angles. And based on this fact, we also know that the ratio between these points, and this is more. I think this is more intuitive than the angles. The ratio between these two sides. So in this case, it's between. Oh, I should label some points. So we have ABC, and then we have D is there. E and F. And we can say, but we can prove that this side, the ratio between this side and this side. And so this to that, I have the same proportion as this side, like from the common point B and E, this shorter side D and F. That's one thing we have learned, and maybe not, but I think you can see how this works. That's all what we have there, and that's the fact of the life. It's not difficult to prove, but I think it takes some work. And yeah, that's a nice fact about similar triangles. And then we have the Pythagoras theorem, which states that if you have again, if you have a right triangle here, size A, B, and C. So we label these variables as the lengths of these three sides, where A and B are the sides that are adjacent to the right angle. This angle, and C is the opposite side. Right then, you are supposed to look at the triangle in the middle. Then we have the relationship between these three sides. A square plus B square equals to C square. The sum of the square of the side that is next to the right angle is equals to the square of the opposite side. There are lots of ways to prove this theorem, but that's not the focus of the part, so we're just gonna use this fact. You can Google it if you are curious. Okay, once we have these two facts, and these two facts are enough to give a proper definition for the trigonometry function. But before we get into the details, let's see what kind of problem we will solve. And so first we have the problem about the pedal. If you move something up and down, we want to find the relationship between the height, the angle, far around the circle you have moved. And you can solve this, you can use this kind of this function, this trigonometry functions in other places. Oh, still haunting your dream. I have lots of trigonometry memes. You can ask for more. You want to, yeah, before learning trig, you sleep soundly. After you learn trig, everything becomes triangles. I'm suspicious. Okay, so the first problem is about the height. This is the classic example where don't worry about this guy. Where you are trying to measure the height of some object is too high to climb up. Right, the way you try you want to measure this pi tree, but it's too high. I mean you don't have a high enough ruler or measurement tool to use. And so you can approximate using a triangle or using similar triangles. And the way we do it is we look. this is fair. Like you put your head on the ground, look up. But then let's think of it using this model instead. When you look up to the top of the tree, maybe use your finger or any kind of tool and to track the position between your eyes and between your eye, your finger, and the height, the top of the tree, the tip of the tree. Let's see that. That's your hand, the last one, and then based on the height of your hand, let's say it's that. You can now you just contract two triangles. We have the original triangle, which is the large one. It's this unknown height, but it has this known distance, and we can measure distance more easily. And then we have another object, which is the height, or the object of your hand. You can measure the tip to your head, because we need to use your head at a level. If you don't want to like put your head in the ground, we have this orange triangle. Then we have this purple triangle as well. It's gonna be some A. So once we have these three sides, this height, this distance, this small height of the object, then we can. Sorry, we don't have this. Yeah, we don't have this, but we have this small distance. Because you can measure the distance from yourself, from your head to the bottom, the position of your thumb of your hand. And once you have this 1, 2, and 3 pieces of information, you can use the similar triangle and then determine the height of this tree. And the formula is going to be something like the. Well, we know that this small height over the smaller distance is equals to this higher part over the longer distance. So you compare the ratio between the two with same two corresponding lengths. It is a vertical versus horizontal, so we have to find the ratio of the vertical versus the horizontal as well. So we have this relationship there. And since we know these three variables or these three parameters, then we can find what is the value of h is. But then you can see that in the left hand side we use the relationship between the height and the distance. Like this height A and this small distance D of A. But this could kind of be arbitrary. In the sense that you can like extend your hand outwards or you can move your hand in, but you still get the same ratio. Yeah, yeah, I can do that. Imagine if you move your hand closer or you move your hand further, you still get the same triangle, the same ratio. And so that means this A and this height and this distance doesn't matter. And what matters is actually the angle. And the actual parameter here is the angle. So once we know the angle, we can determine the ratio of these two lengths for sure. So that's gonna be corresponds to the angle. If you give me the angle, I can give you the ratio without having to determine the height in the length. And how do you find that? Like how given an angle, how do you find the ratio? And of course, we're gonna have to refine the function. Given z some variable zeta as the angle here, we can find the ratio. Need the function that does that for you or for us. Given an angle, we can find a ratio between two sides. Once we know that all we need is the angle, then you don't have to worry about like moving your hands up closer or moving away. As long as your arm is fixed in the same at the same angle, then you are good. You can use that angle from your arm to the left, to the ground level, to determine this height. And so that's the idea of why we need to define such functions. Why we need to define trigonometry functions. That's the first one. Oh, and then we will see in a moment how to accomplish these things. Next we have force. This is physics stuff, and it's a little bit more complicated, but we will need to study this a little bit in terms of vectors later in this class. So we have an object. This is an object. You can think of it as a metal ball. I don't know why people love metal. Maybe they are heavy or something. And there's the ceiling up here. And then you put some kind of pivot part or something on the ceiling and connect that pivot to the ball. And as you can see, the ball is kind of floating, and because it is moving, it is slightly to the right. So you might have to like grab it for a moment to make it into this position. But then once you release the ball, and the ball will move to the left, and because the weight is pulling it down. But since it is just a rope, it's not a straight line. So the weight from the ball will pull the rope down to a more natural position. And if it bounces back and forth in what we know as a pendulum movement. Yes, the old clock. I don't think anyone has one in the house nowadays. The old clocks use this kind of pendulum movement to measure time. And the way physics works is there is only one force that takes the ball down, which is of course the gravity. It's the same force as the one that is taking everything down. But the ball doesn't move down, right? Because of the rope. It's trying to pull it to the. It's trying to pull the ball to the left. Yeah, left. Yeah. Right, so the force is down, but the tension of the rope is trying to pull it to the left. And so the ball moves to the left instead. And then the way you compute the movement or compute all these forces is you need to change the force here. And somehow into the force that move into the appropriate direction. There must be a way to change this force to the other force. And again, if you draw only two lines, it's not obvious what it is, right? But if you connect it and make a right angle, and then define an angle somehow, then you just get yourself a new right triangle to work with. And so now everything works. You can do all the maths like once you know how to construct this kind of triangle. Oh, and by the way, the force doesn't just like disappear and move. It's not like you can move everything anywhere. And the force is actually distribute or split into two forces in two different directions. And again, we will learn this when we get to the vector part. But that's the idea. And we use the trigonometry to change this force to the two other forces to split them out. And we can do that if we know how to find this right triangle and find the ratio between these two sides. And next one is, of course, maybe this is more familiar. If you play games or if you do anything, if you, even if you are the way you are looking at the screen right now, the screen is using this kind of rotation. Rotate my hand from this position to that position, and then the screen has to knows how to compute the movement of my finger, place it into the correct position. That's what we use a lot in computer graphics, computer software. And the way this works is you can imagine the screen as a plane. Any point on the screen has some kind of coordinate. Let's say this is like 3, 4. And so you know, okay, you need to paint like pink color at this point. Yeah, but if you rotate this by some angles, let's say by 45 degrees, color clockwise, and so it's moving this direction. Then you need to know how to determine like where this point should go to. Maybe let's make it like this stick figure. If you rotate him and this head go there, the body is not gonna be straight up because you rotate it, so it's gonna be something like that. And so the task or the job for the PC is to determine where exactly you move each of these points. If you zoom in, you need to move each of these points, like for example this point, to somewhere here. If once you rotate it, so it's gonna, if you trace it, then it should be like that. Which of course you can kind of trace it physically. I think about moving the object physically. Or like here, like there, moving it in the software. But the thing is, also, you need to do it for all the points, not just the head, or not just the leg, or not just the body. So to apply the same rotation to all the points, like you better have a formula. When I give you these 2 points, and you can split out, you can determine immediately where that point should go after this rotation. And that's the formula. You don't have to freak out yet, because we need like several steps before we can understand what this formula is trying to tell us. And so we have the point x and y. If you rotate it by some angle, theta, and that's the coordinate of the new point. Of course, you can use this formula. You can just type it in the code, and everything works. But it should be better, right? If you get an idea of why the formula looks this way. And is there any better formula, like better way to write this in terms of x and y's? So I don't have to like memorize where does cos go, where does the sine go, is it plus, is it minus? We will learn that there is actually a magic formula, or a magic, maybe we will call it matrix, you know, in a few weeks. But that's the way to rotate a point, by computing just a single formula here. And to understand that formula, we need to know trigonometry first. What is this sine, or what is this cosine? So that's the third problem that we can use the trigonometry to solve. Maybe you have solved this already, but maybe it should be a good refreshment. So after all these problems, we will start to define that in a moment. Yeah, but not this one. So see you in the next section.